Hello, everybody. This is March Papers I Love. This is year 3. We were going to have cupcakes, but we're going to owe them to you and have them next month because, all right, so it's been 3 years. Thank you to all of you. I think Bob has been with us since the very beginning. So Bob is one of the old-timers, but not because he's old. It's just because he's been here attending. I think there's more of you that actually have been with us from the beginning as well. Thank you so much. We really try to make sure that we create a community and an environment where everybody gets a little bit of something. This means that we are still working on the schedule and the speakers for this year. So if you have any ideas, if you want any topics or anything else, just let me know. And I'll do my best to get speakers for that. And also, if you want to do a mini, we're covered until May. So if you want to try and present a paper, it's 10, 15 minutes. We'll help you out if you've never spoken before. So let me know. We have a Slack channel as well that if you want to join, I normally post announcements of when the meetings are going to happen and volunteer people for talks there as well. So know that this may happen if you join. So normally the way that it works is that we have 2 speakers, one for a mini, one for a full-length talk, and I give an introduction, and I also make something fake about them. So let's get started. So I'm going to introduce Matt Adereth. Matt builds tools and infrastructure for quantitative research at 2 Sigma. He previously worked at Microsoft on Visio, focusing on ways to connect data to shapes. In his spare time, he builds ergonomic keyboards using Clojure. When he was little, Matt dreamed of being a world-renowned magician. Let's give it up for Matt.
Thank you. All right. Hi, everyone. My name is Matt Adereth, and today I'm going to be doing something a little different. Usually, Papers We Love, people present a paper, or maybe like a series of papers that are related to some topic. Instead, I'm going to present a journal containing a bunch of papers, and the papers have nothing in common other than the fact that they were in the same journal. But I'll tell the story of why I'm doing that, and hopefully we'll all have fun, because I had fun. So specifically, I'm going to be presenting the Computer Journal from January 1965. It was published by the British Computer Science Society. And the way that I found this paper was, this journal was through this paper called A Simplex Method for Function Minimization by Nelder and Mead. Maybe you've heard of it. It's sometimes called Nelder-Mead, which is fun to say. Sometimes it's called the amoeba method, for reasons you'll see in a little bit. And what it does is it tries to solve this problem. This is the mathy way of writing the problem. So we've got some function f, it takes some parameters, and we want to find the value of the parameters that minimize that function. And this happens all the time. In engineering, we want to find the most efficient design that minimizes something. In business, maybe we want to find just the right set of knobs that are going to maximize our profit, or our JVM settings that give us the best throughput, whatever. These algorithms try to solve that problem in a general way. It also happens a lot in machine learning, and you may have heard of things like gradient descent. Those techniques are great when you know something about your function, like you know the derivative, you know which way to go to get a better result. But this technique works on any function, even if you don't know what it is and you don't know its derivative, just a total black box. So here's the paper. It's very short. It's just 6 pages. And the first 2 talk about the algorithm. Then the rest of the paper shows how the algorithm performs on some benchmarks. One of the benchmarks is one of my favorite functions, the banana function. This is my favorite thing in Google, that you could just type banana function and it gives you the banana function, the Rosenbrock banana function specifically. So you can see an example of something that we're trying to optimize, where this one is really tricky for algorithms, so it's used quite often as a test case. And this is a 2-parameter function that was trying to be optimized. The paper doesn't have any pseudocode in it. This was before pseudocode was really a convention. flowcharts were kind of the way that a lot of these algorithms were written out. Don't read this, sorry. I meant to say don't read this. It's going to distract you. It's also not really clear. The only reason I included it was because I really like that you could see that the arrows were all hand-drawn, and it gives you this, like, you know, personal connection with the authors, or maybe they're grad students. I like to pretend it was both the authors doing it together. That's my headcanon. So unfortunately, the algorithm was laid out in that table, or in that flowchart, and it's kind of hard to understand, but it's actually a really clear algorithm to understand visually, so that's how I'm going to explain it. What we're going to do is we're going to optimize a function that has two parameters. So one of them is going to be on the horizontal axis, one of them is on the vertical axis, and there's some value of the function that maybe we would see as a heat map here if we knew what the function actually was. So the way it works is you start with a simplex. Now, a simplex is a fancy way of saying triangle. More specifically, it's n plus 1 points in n dimensions. So in one dimension, you have 2 points. It's a simplex is a line segment. In 2 dimensions, you have 3 points. It's a triangle. In 3 dimensions, 4 points. You get a pyramid or a tetrahedron if you're fancy. 4 dimensions, I don't know. Maybe a time pyramid or a color-changing pyramid, depending on your flavor of synesthesia. But let's just look at it in 2 dimensions, because that's the easiest to see. So what we do is we pick 3 points, pick a triangle, and we evaluate the function at each of the points. And then we see which one was the worst, or in the case of minimization, which one had the highest value. So let's say it was this one that I'm coloring red. Now, the intuition here is that we've got these 3 points, and we know that this one's bad, so maybe we could think that, like, this side of the line is bad, so let's try the other side. So what we do is we reflect that point around the center of the other 2. We try this point. And there are 3 possibilities now. Either this new point is the best of the 3, the worst of the 3, or neither the best nor the worst. So if it's neither the best nor the worst, what we do is we find the new worst of the 3 and recurse. We just flip that one instead. If it's the best, we say, all right, this was a good direction to go. We were over here, we're trying over here now, it was better, maybe we should keep going. So we do this expansion, and we try this point. If this point was the best, we use this new stretchy triangle and recurse on that. If it wasn't, we just use the one with that's green here. If it was the worst, then we're kind of not sure what to do, because it sucked on one side, it sucks on the other. So let's just get closer to the line. So we do a contract and recurse using that triangle. That's the whole algorithm. It's really best seen visually like this, and fortunately the Wikipedia page has an animation of it, so I didn't have to create this. And you can see that when you keep doing it over and over, this triangle moves, and it kind of finds the optimum, and eventually kind of shrinks and contracts on it, and you have some stopping condition, which could be a bunch of different things that we're not going to talk about. This is why it's called the amoeba method, because it kind of looks like an amoeba slithering around. And that's Nelder Mead. There's this great paragraph in here that says the simplex method is computationally compact. It's fewer than 350 instructions on the Orion computer without final printing, because printing is expensive and they don't want to skew their benchmarks. And it's all addition and subtraction and a little bit of multiplication. There's no division. Division is really expensive. So super efficient. And this efficiency and simplicity has led to this algorithm being used a ton. It's used to this day as like the default optimization method in most math libraries, or at least it's available in most math libraries. And it's just ridiculously effective. So it's lasted over 50 years, and this paper has been cited over 24,000 times. It's one of the most cited papers in computer science. Possibly due to this last sentence, copies of the routine written in extended Mercury autocode are available from the authors. So it's open source, reproducible research. 1965, they were doing it right. They've got their benchmarks that they're publishing, if only today. All right. So I lied before when I said that it was 6 pages. It's actually 5.5 pages. And I had used this algorithm a bunch before, but I had never read the paper. And I went and I was doing some archaeology, and I read the paper, and it was cool. But the real treat was on the last page. Because it was 5.5 pages, the last half of the last page had something that was very surprising, which was a letter to the editor from this guy, Chris Strachey, who is a somewhat famous computer scientist. And he did a bunch of interesting things. This is the guy who coined the term currying. That's cool. He didn't invent the concept, he just coined the term. He also wrote the first checkers AI, and he invented this language CPL, which he uses in his letter to the editor. He writes this story. He was riding the train with Alan Turing, no big deal. And Alan was telling him about the halting problem, as he does. And it was great. He learned about the halting problem and then promptly forgot it. Forgot the proof of it, and he remembered that it was really cool and a little weird, and he thought it must be horribly complicated, and then he remembered it and got really excited and couldn't find it published anywhere. So he decided to write this letter to the editor to share the proof, because it hadn't been published widely. So he writes the proof on the right-hand side here in CPL, the language that he invented. It's pretty simple. You assume that there's something that solves the halting problem, call that T, and then you write this program called P that just loops, and its loop condition is if T says that P halts, then loop. If T says that P loops, then halt. It's a contradiction. It's proof by contradiction that T can't exist. That's this well-known piece of folklore among programmers. So I read this, and I was like, how is this next to Nelder Mead? That's weird. Like, we don't have that today. We don't have numerical method papers alongside deep theory talking about the halting problem. Like, what journal was this published in, and like, what else was in it? And also just imagine getting this journal in January 1965. I don't know if anybody here was reading journals back then, but learning these two things, having your mind blown left and right. So there's got to be other good things in here. So fortunately, all the other papers are available and more. So here was the cover that I was able to find, and I was able to find all of the advertisements that were in the Computer Journal, January 1965, and it's a good place to start because they're kind of fun. Here's one from NCR for their new language, Language H. It's as genuinely machine independent as COBOL, and uses English words. It was a flop. It doesn't even have a Wikipedia page. Sad. Also, just for some context, they were using punch cards. Here are tape punching machines. This monster over here, in the bottom right, it's 300 characters per second. Yeah. Imagine. When executives talk air conditioning, I love this one. I don't know if you can see, but there's a picture of a computer room there, and you know it's a computer room because right next to it, it says the words computer room, period. It's got these 3 dudes chilling in the computer room while these 2 execs are puffing on their cigarettes, talking about air conditioning. Extreme cooling. There were also job placement advertisements in here. Ready for action programmers. This is like rock stars, ninjas, ready for action. They have openings for able, ambitious men. Not even. I didn't understand this because this is 1965. At the time, my understanding is that programming was like a lot of women. Some people considered it to be women's work. So there was a lot of references to men throughout this. Very little about women. The only women, unfortunately, that I was able to find were in this central vacuum for keeping your computer room dust-free, where there are some women vacuuming it, which is, yeah. But it's not to say that they didn't, that there weren't women programmers and they wouldn't accept papers. They have the notes on the submission of papers for the journal here, which I read because I have problems. Authors' names should be given without titles or degrees. Women are requested to give one Christian name in full to avoid confusion. Christian name is the non-intersectional way of saying first name. And I'm not sure what the confusion would be, but they wanted to avoid it. So, all right, let's look at some of the actual papers in here. Thank you. Yes, so women used to publish using their husband's first names, saying Mrs. and then the husband's first name. Yeah, thank you. Confusing. I could see why you'd want to avoid that. So the first paper that jumped out at me was this one called A Basic Approach to Pattern Recognition by J.R. Ullman. I got really excited because J. Ullman, there's Ullman, Hopcroft and Ullman is the street name for An Introduction to Automata, which is a famous book. He also wrote the Dragon book on compilers. This is not that J. Ullman. That's Jeffrey Ullman. This is John Ullman. This guy, I feel bad for this guy. But the paper was actually pretty cool. It discussed how to do some compression on this data structure that's used in what they call pattern recognition. And when you read the paper, what it's actually about is the main example was doing character recognition, where you have like a handwritten character, and you have it represented as a two-dimensional array of ones and zeros for black and white, and you want to know what letter or number was written there. Which was shocking to me because to this day, that is the go-to problem for new like vision machine learning algorithms, like the MNIST data set. I did not realize that they were working on that exact problem in 1965, so that was pretty cool. The next one that was interesting was this one called Lists and Why They Are Useful. So that jumped out at me, because that's just a fun name. Later I realized it was written by, it says M.V. Wilkes, that's Sir Maurice Wilkes, all right, there's some laughs. Sir Maurice Wilkes, he is a Turing Award winner, won the Turing Award for his work on the ENSAC machine, which was one of the first computers with programmable memory. So here we have an article written by him explaining linked lists, because that was relatively new and a lot of people didn't know about linked lists. So he explains linked lists, explains how they might be laid out in memory, some of the things that they're useful for. His example is representing symbolic equations using it. And you can't, sorry if you can't see it on the left, but he has some examples of these using linked lists representing symbolic equations. And mind you, this is like an intro to linked lists for people in 1965. And he also had some code written in a Lisp dialect for computing the first derivative of such an equation. So this is, how we all probably learned linked lists in Computer Science 101 from Sir Wilkes. So that was fun. That was a nice treat. And then the last paper that I want to talk about, or article, is What is the Use of Operating Systems? Another one where the title just kind of jumped out at me. Oops, let me go back. So you can't see, I'm sorry, but before the abstract starts, before long, nearly all computer users will be using operating systems with their equipment. And this was really an interesting read. I recommend that everybody reads this one. It's only like 6 or 7 pages, and it was really interesting for a few reasons. So one, when I learned about operating systems, it was from the perspective of, here are a bunch of different operating systems, here's how they differ, here are like the parts. Whereas this was from the perspective of, we don't have operating systems, we're using the bare metal, like, why do we want to incur the cost of having an operating system at all? So that was different. And something that was really striking was a lot of the arguments that were made for operating systems have been made over just the last 5 or so years for distributed systems, for like why we need things like Mesos or Kubernetes. And the arguments are exactly the same. So I got a kick out of that. He's also kind of salty and funny. He's got a lot of disdain for people. There's one part, it's generally recognized, except in a few last pockets of resistance, that there is something to be gained from the use of languages of higher level than those of computers themselves. And it's still kind of debated. It covers a lot of things. It covers interrupts and virtual memory and use of file descriptors for resources, and a lot more. It was cool. It was a good read. I recommend it. And just to end, I'm going to end with the last sentence of this paper, where he said, "It is to be hoped that it will not take too long for the economic situation to allow us to put man's time at a higher premium than that of machine," which sort of still waiting for, but you should read this one. So that's it. Thank you very much. I hope you had fun. Sure. Could do questions if anybody has. Yes. Sorry, what? I think that the way that they are arguing that it has no division is that would be like multiplying by 0.5. Yeah. So if they were dividing by some number that they didn't know in advance, they couldn't get away with that trick. Yeah. So the question was I able to get a copy of the complete journal? How? Not a physical copy. Most of the papers, actually, all of the papers are available online at the Oxford Journal behind a paywall. 2 of them are available for free. Some of them I was able to just find through Googling, as one does, by just adding PDF to the end of the paper's name. One I wasn't, and I had to get it through a subscription, which was the why lists are useful one. And for some reason, that was the only one that was not re-typeset, and it was in the original, the font. Yeah. All right. Well, so that's not making it into the mic, so that's not going to be recorded for. But you can add the comment, and we can all. Sci-Hub. All right. Thank you.
Okay, so while Tom gets ready, we'd like to say thanks to OpenDNS for hosting us today. Thank you so much, OpenDNS. Woo. And I'm going to introduce Tom while you get in your setup. Okay, so Tom Santero loves books and people. He's an organizer, an in-the-trenches programmer, and he's always hungry for more. In his spare time, Tom makes life-size statues of pop stars, and his material is butter, and his current muse is Nicolas Cage. Has to be because of the hair, right? Nicolas Cage? Yes.
Yes.
Yes, good. Let's give it up for Tom.
My name's Tom Santero. I work at Postmates on the infrastructure team. We're hiring, obviously, because this is San Francisco. So if anyone wants to help me make sure people get their burritos on time, talk to me after. Want to clarify that I do not make statues of celebrities in butter. Yeah, I don't think anyone believed you. So yeah, I love Papers We Love, this meetup. I was telling some people earlier, I actually first heard about it with the very first one in New York, which happened 3 years ago. I didn't get to the first one, or the second one, or the third one, but I finally made it to the fourth one. And I was really excited because, you know, I love papers, and all you nerds make me feel much better about being a nerd myself. So this is my second Papers We Love talk. I was walking over here from the hotel earlier, and I was thinking the first talk that I gave at Papers We Love was actually about indecision, and this paper that I'm about to present is about making decisions, so if I ever give a third one, who knows what it'll be about. So show of hands, who here has actually ever played Texas Hold'em? Are you guys any good? I started playing in 2003. I was 17. I started playing online. This is back when it was still legal. There are still places where you can, from the United States, actually play online. Hopefully we could change the laws. But I found this paper interesting. I wasn't going to do this paper initially. I was going to do something completely different. But Inez pinged me a couple of weeks ago to confirm the date, and I had literally just read this paper. I'm like, yeah, let me do this one. So it turns out, after reading it several times, I doubt any of you actually read the paper because no one ever does these things, right? It turns out that there's not a whole lot that you could get out of this paper just because the authors repeat themselves and they don't really go into the nitty-gritty details of the algorithm, but rather just vaguely describe what they're doing. But I've labored to extract value from that and present it to you in a way that, if anything, for the half of you who raised your hands for when you said that you played Texas Hold'em, that maybe it might help influence the decisions that you make at the table or online if you're playing that way. But without further ado, let's get started. So, Texas Hold'em obviously originated in Texas back in the early 20th century. It didn't actually make it into the casinos in Vegas until about the mid-50s or so at the Golden Nugget, which I'm not sure if still exists or not. And if it does, it's probably trash, like it was back in the day. It literally had sawdust on the room of the poker floor. But Texas Hold'em itself is a variation of poker, and it's the most widely played card game in the world. For those of you who aren't familiar, these are the rankings of the various hands. We play it with a traditional deck of cards, 52 cards, 4 suits, 13 cards per suit. And the values are 2 through 10, Jack, Queen, King, and then the Ace, and all in ascending order there. So you can make a pair, 2 pairs, 3 of a kind, basically 3 of the same kind. Flush, where all of your cards happen to be the same suit. A full house, which is a 3 of a kind and a pair. 4 of a kind, 4 cards are the same. Straight flush and royal flush. So just so that there's no ambiguity whatsoever, I do want to go over a little bit of the dynamics of the game before we actually start getting into how these people have actually programmed a bot that's different from other bots that has successfully beat some of the world's top poker players in a recent experiment that they conducted maybe about 7 months ago at this point. So traditionally, you could play with up to 10 players. In this particular paper, we're concerned with a variation of Texas Hold'em called Heads Up, which is simply 2 players playing against each other. Gameplay moves clockwise from the position of the dealer, and the dealer position also moves in a clockwise fashion after every hand. So as you can see here in this particular diagram, the D represents the dealer's position, and the 2 seats to the left represent what's known as a small blind and a big blind. So there's a minimum wager that's required for each hand, and those are going to be preset at any given cash game, which is basically sit and go. You could get up and leave at any time you want. In this particular example, the blinds are 1, 2, so starting from the dealer position, the small blind has to put out $1, the big blind has to put out $2, and then the next seat over, just to the left of the big blind, is responsible for either folding, they could call the big blind, or they could make a raise. Similarly, with every other position, until we get back to the big blind, who has a final option to make a raise if they'd like to. Everyone clear on the dynamics of the game? Cool. And yeah, as gameplay goes on, the dealer position will move, so on and so forth. So what's interesting about Texas Hold'em as a game that you would want to try to develop an algorithm that could beat human players or even other computer players is that unlike a lot of the more recent things such as AlphaGo, where we're playing games using an algorithm that could effectively solve the game, we're dealing with incomplete information. And what that means is that each player is dealt 2 cards that are face down that only they get to see. Those are known as your hold cards. The way that the game works is that after the first round of betting, we get what's known as the flop, which is 3 cards that are dealt face up. And those are communal cards, public cards that everyone gets to share. There's another round of betting. Then we get the turn, which is another card, a 4th card, also known as 4th Street. Another round of betting ensues, and then if we make it this far, we get the river, or 5th Street, which after another round of betting, we'll see the showdown and the dynamics of the game and the probability function of whose cards are no longer in play. It's simply whoever has the highest hand using their 2 cards and the 5 public cards available on the board, they will win the pot. And the pot is obviously all of the money that's been put in. And we keep score in Texas Hold'em by counting big blinds. So our big blinds is obviously the total number of chips that we have divided by the cost of big blind. In our previous example, it was $2. So if I were to have $1,000 in front of me at $2 big blind, I would have 500 big blinds. Or in this paper, the way that they rank it is millibig blinds, which is just a thousandth of traditional big blind. So yeah, before we get into the algorithm example, I just want the algorithm itself in the paper. I want to give you an example of traditional gameplay. This is actually something that happened to me a couple of weeks ago. I went up to Cheyenne, Wyoming. I live in Colorado, so it's actually kind of a short drive for me. And I'm an idiot because, look at me, I'm 5'8", like 150 pounds, and I go to play these 6'5" cowboys that work on oil rigs after they get paid. I'm surprised I haven't been jumped yet. But here's an example of something that actually happened. I was sitting there, and there's this cowboy directly across from me, big white bucket hat, belt buckle, knuckles that are bigger than my fist. And I get dealt 6-5 suited, 6-5 of spades. It's a decent hand. In the top right, I've given you the odds on statistically what my probability function is of, on the flop, getting a 3 of a kind, a straight, or a flush. So this isn't heads up. There's other players at the table. But with a hand like this, I wanted to raise so that anyone who had a weaker hand or a hand that had a higher probability of actually hitting something on the flop, I wanted them to fold. So I made it expensive. It's a 1-2 game. I raised to $20. All the other players fold except for the cowboy, who raises to $45. And I call him because I've got $20 committed, and sure, why not? So here's the flop. 3-2-4, rainbow, which means that there's no one set suit, so any possibility of flush is, for the most part, out of the question. I flopped a straight. I hit a 75-1 chance, and I'm feeling pretty good about myself. There's about $90 in the pot right now, and I bet $65. Cowboy calls me. So if you were to call me, I'm thinking, what does he have? By virtue of the fact that he raised before, he raised me pre-flop, I'm thinking that he probably has a pocket pair, 2 cards of the same type. And so my $65 bet felt pretty safe. The turn comes, 4th street, it's a jack. So right now I'm looking at the possibilities in my head, because I'm not a computer and I can't calculate at the speeds that the algorithm that we'll be discussing in a bit can. I see 2 hearts, so the possibility that he has 2 hearts in his hand and on the river he might hit a flush is one possibility that would provide him a winning hand over mine. I think I'm still good though. I've got my straight, and I've also got the highest possible straight according to this board. So I go all in. I bet all of my chips, about $420 or something about that. He calls for a little bit less, 300 or so. So the pot's, roughly $1,000. Who here thinks I made the right move? Who here thinks I made a ridiculous move by putting all of my money at risk? Inez and someone else I don't know. All right. Statistically, this was the best move to make, shoving all in. So when you go all in, you get to see what the other person's hand is. You both flip over your hands. He had pocket 3, so he had, trips, and I'm beating him. He has 4 possible cards that could win. Another 3 to give him 4 of a kind, or any of the 3 remaining jacks. So he's got about a 10% chance to win. Yeah. So he won that hand. But I'll play it the same way over and over again. And if I were deep stack, I think I would probably do the same thing, but we'll figure that out. As an aside, I shortly after left to get up and go to the bathroom, and when I got back to the table, he was gone, so that kind of pissed me off. Because I wanted a chance to win my money back, right? But he hit the lotto. So, deep stack, expert level artificial intelligence and heads up no limit poker with a laundry list of authors. So this paper, it's not really novel, it's iterative. If you play online right now, you'll probably find yourself in situations where you think you're playing up against a bot, and chances are you really are. This paper is also a little bit long-winded for what it presents, and like I mentioned earlier, I'm going to try to extract as much value out of it based off of my limited knowledge of math, as well as my not as limited knowledge of poker, but I am by far not an algorithm that could beat the best poker players in the world. So, like I mentioned earlier, Heads Up is a Heads Up Texas Hold'em. It's a game of imperfect information. We need to reason about the same sorts of scenarios that we might with a perfect information games such as Go. And the way that we do that is in imperfect information games is a concept of recursive reasoning. So essentially, our actions are going to inform our opponent's actions, which are thus informed by our past actions, and so on and so forth, recursively. The thing is that in order to reliably and provably beat the game over and over and over again, to effectively solve the game, we can't really reason about any one given action in isolation because it's all dependent based off of variable change of the chance of a new card coming out, as well as the information that we gather from our opponents based off of the actions that they're actually taking. So, in Heads Up No Limit Texas Hold'em specifically, we have a total of 10 to the 160th total possible decision points for any permutation of game state, compared to in Go, 10 to the 170th. So we're sort of on par with perfect information games, except, again, because we don't have perfect information, we can't pre-solve the entire game beforehand and then sort of just apply those strategies. Pre-solving the entire game is still, again, very common, and it actually makes money if you build one of these things and put it online. But there's also a concept of solving it via abstractions and counterfactual regret minimization, which is pretty interesting. In fact, a paper on CFR would be really fascinating for anybody who wants to do a papers we love in the future. The idea between counterfactual and regret minimization is, if I were to give you an example, rock, paper, scissors, Rochambeau. Let's say I'm playing against Inez and Rochambeau, and she throws scissors and I throw paper. I'm going to regret that I threw paper because she won. And so what I'm going to then do is take all of the possible things that I could have thrown, rock, paper, or scissor, and I assign values based off of what my past experiences. Obviously, I would have loved to throw scissors as well, so that we ended up in a draw, or possibly even throw rock to crush her scissors. And so we play again, I learn something else new, and I continue to assign more and more values. Over time, I could have basically a stochastic model of when in any particular situation, I could, with some certainty, actually beat somebody in rock, paper, scissors. And I think it was the New York Times in 2014. They actually built a CFR model for rock, paper, scissors that you could play against online, and it beat the hell out of me. So it's a pretty effective model, and it takes into account what your opponent does over time. But despite these two approaches being a dominant approach, the authors of this paper decided that they wanted to actually have their computation focus on very specific isolations as they occurred. So it's time for some game theory. John Nash, Nash equilibrium. So a group of players are said to be in a Nash equilibrium if each of them is making the best decision possible, taking into account the possible decisions that their opponents could be making, and such that neither player's decision remains unchanged. They're said to be such that their decisions remain unchanged in a way that not making any change will result in an improvement of one of the other. They're said to be in a Nash equilibrium. So formally, if we were to let S and F represent a game with n players, we could say that our strategy for any given player is such that we have a combination of all the total set of strategy profiles. The strategy profiles also have functions of expected return, or our payoff function, which could be represented as f of x for any x that's a member of our set of strategies. So a strategy profile, again, for a set of strategies describing all players' action for the entire game. If any player chooses a particular strategy, then naturally our payout function is going to be f sub I for that player of x. So it follows that for all possible strategies for all players, it will produce a Nash equilibrium such that for all of the individual players picking a particular strategy of the total strategies that exist, the expected return and the payout function for one player and the other player is always going to be greater than or equal to all other strategies for that player and the other player's payout function. It's a little contrived, but again, essentially it says that the strategy profile will produce a Nash equilibrium so long as that no unilateral deviation, no single player deviating from this strategy can make a change to how they play and have it result in improved expected payout. Is that pretty clear? Cool. Yes, because they're in equilibrium. There shouldn't be. Yeah. Yeah, the X's are going to be different. Yes. That's what the stars are supposed to denote. Yeah, I apologize. Yeah, it was a little confusing for me at first when I was like looking up the actual formal proof. But yeah, so like the strategies should be interchangeable, but the end result should be effectively stalemate. And so, you know, just to drill it home, you know, the prisoner's dilemma, you know, let's say, I don't know, RZA and GZA from the Wu-Tang Clan are planning a caper, right? They're going to take back the record Once Upon a Time in Shaolin that they sold to Martin Shkreli, which is available in the contract. They could plan a caper one time. But let's say, they get busted during it, and the cops put them in different holding cells, and they say, okay, well, if, we got you, you're going away for 6 years. But if you flip on your buddy, you walk free, and he'll have a 10-year sentence, and vice versa. So the idea is that the Nash equilibrium here is going to be the bottom right quadrant where they both lie. They say that they weren't involved in it. They both get 2 years, and that's the best maximum possible strategy that they could employ, given the knowledge of the other options that are available to them. This was expanded a little bit further. 1956, I believe it was, Theory of Games and Economic Behavior, John von Neumann and Oscar Morgenstern. And they basically took the idea of Nash equilibrium, and they said that a mixed strategy, Nash equilibrium, will exist in any zero-sum game involving a finite set of actions. So a mixed strategy is basically the ability to make different decisions based off of different information available at that particular time. So instead of always lying or always confessing to the crime, no matter what, we're actually able to take a look at what the potential penalties are and then readjust. So this actually kind of fits to the game of No Limit Texas Hold'em, because obviously it's a zero-sum game. There's got to be a winner and there's got to be a loser, and there's a finite set of actions that we could actually perform. To give an example, in a particular game of poker, say we're dealt pocket kings. The way I'm going to play pocket kings before I see any of the cards on the flop is pretty strong, because it's the second highest hand that you could get dealt pre-flop aside from pocket aces. So let's say that the flop comes and it's king 5 jack. I'm feeling pretty good. I just flop trips or whatever. So I'm going to probably bet and bet hard or call, or whatever the strategy that I'm employing is. But just to give you an example, it significantly changes if we were to see an ace instead of a king on the flop. Any player that I'm playing against, any opponent who happens to have an ace in their hand, has got me beat in this particular case. So getting back to the paper for a moment, we have this diagram. It's representative of the various stages of action where the nodes in the graph that are colored teal and red show what our actions or decisions can be based off of the private information that we hold and the public information that's available to us. And the green nodes present new public information coming into play. And by building trees like this is effectively how DeepStack goes about solving or attempting to solve how to make a decision at each stage of the game. So, good players and bots like DeepStack, we're concerned with exploitability of our strategies. So what that means is that any strategy is how I'm going to play a particular hand that I'm dealt, based off of the actions that I see in my opponents, as well as the probability distribution of whether or not the cards that I'm holding are going to make a hand that's stronger than the other possible hands that I could see on the board. What DeepStack attempts to do is provide a low exploitability style of play for each consecutive game in such a way that when playing against any other player, we seek to establish a Nash equilibrium, and when there's some sort of deviation from strong strategies, that's when it's able to take advantage, and over a long enough time, the results show that it's quite successful. We'll get to that. So there's a concept of range. A player's range is basically what they're willing to play at any stage of the game, and for how much. And determining a player's range is very difficult for a human to do, much easier for a stochastic function run by several GPUs. And what we want to do in our strategy in DeepStack is actually try to determine what our players actually, DeepStack does not attempt to determine players' ranges like many of the previous approaches to trying to solve the game of Texas Hold'em does, but rather, as we'll see, it takes a different approach. But for humans, this is effectively the best that we could do because we can't continuously resolve. Kevin has a question. So the question is, when I say probability distribution over a range of public actions, is that for every card that the player could have? Is that what you? Right, right. Yeah, so that's what the past approaches were. Like, if you have a pair of aces, you always raise, at least pre-flop, you know? But, you know, if you were to try to pre-compute the game before you actually saw new public information, such as the flop or the turn or the river, the approaches that didn't do the CFR, but tried to brute force the game as a whole and always play according to certain strategies, they would play those aces hard all the time. And you actually find players like that in casinos all the time too, and they actually end up giving you a lot of money if you know how to exploit them. But the idea is that we want to calculate the probability distribution for what we're holding versus what the public information is in the terms of the cards that are available for all of the players, the flop, turn, and the river, as well as what our opponents actually been doing as far as how strong they're betting, if they're just flat calling, or if they're raising us, and so on and so forth. So yeah, is that clear? Okay, cool. So again, DeepStack, it actually attempts to establish it attempts to solve for a Nash equilibrium at every stage of gameplay for every hand. So if we were to assume the best response strategy of our opponent, meaning they're going to try to maximize their potential value for any given situation, that's when attempting to try to solve for a Nash equilibrium for DeepStack, that's how it actually ends up making its money. So how does this do this? Limited exploitability via heuristic search. So we have our starting local strategy, how we attempt to play the hand that we've seen before. DeepStack uses two neural networks that were trained with millions of hands. There's a flop neural network and a post-flop neural network that they've trained, and they use two different ones for they used two different neural networks for this simply because it collapses the total state space for the possible iterations that you could see after the flop. But what they do is, having seen that, okay, I know what my probability distribution is of, you know, hitting trips with a pocket pair pre-flop, and then once I get the flop, what it does is a depth-limited look-ahead search of the possible subtrees for all of the various scenarios that could exist in this particular game. So we know what we have. We know what's on the board. We don't know what our opponent has. So what we want to do is, to the best of our ability, approximate all of the possible counterfactual values for our opponent. The counterfactual values are, if they have this, then with this particular board, they have the possibility of making all of these hands with these possible future scenarios and are likely to bet in this particular way, and so on and so forth. So what they do is that, again, for every stage of play, for flop, for the turn, for the river, they're going to resolve for all of these potential values. So again, we have our initial state that's determined by our particular range of play, the cards that we're willing to go into, and how we're going to act on that. But then, for every next action, we completely disregard every reason why we came to this particular point, and we say, okay, is it actually possible for us to resolve the game, determine what our previous strategy was, as well as determine a strategy for moving forward? And the way that it does that is by taking a CFR algorithm, and so similar to past approaches, but it takes it provides input as our range and again a complete vector, a total vector of all of our opponents' potential hands, and we're going to update our range and update what we expect our opponent could possibly have, and what their actions may be with resolving. So they give the solver a couple of rules that it needs to go by according to every time that it's actually running. So if our opponent's making an action, we do absolutely nothing to change our mind of the state of the world. But what we do for our own action, if it's our time to bet, call, or fold, we're going to completely replace all the known vector of counterfactual values for our opponent with the strategy that we've just used for any particular action that we can make, and we're going to apply the probabilities of what we have for our hand in order to determine what our particular action is. That's not as interesting as what happens when there's a chance action, which is another card comes on, which is completely uncontrollable. So we recompute what our opponent's counterfactual values are going to be, and we update our own range by eliminating all hands that are now considered impossible based off of the new information. So does this by searching sparse look-ahead trees, and those are trained based off the neural net that they constructed. They call it intuition in the paper, which I buy maybe 70%. I'm not fully on board yet, but I suppose intuition from the human standpoint is, subconsciously I'm doing the math, and based off of my past learned experience, I could approximate, but that's effectively what they're doing. So the look-ahead trees have the public state of the players' ranges for ourselves and our opponents, the pot size, and the total public cards that are available on the board. Effectively, what the input is describing is any given situation in any poker game ever, and it then just attempts to solve that against the probability distribution of what we actually know is in our private hand. The output is what gives us, according to the current public state, the expected values of any potential hand that our opponents could be holding. And yes, and so like these trees will be traversed for any permutation for any hand, querying the evaluation function for all the various different possible ranges. And what they do with the look-ahead trees is that they reduce the total number of actions that can be taken to just 4. Fold, call, 2 or 3 bet, or all in. 2 or 3 bet, a 2 bet is just the second possible bet in a hand. A 3 bet is the third possible bet in any particular game. So if it gets to the point where it wants to bet again, it's just going to shove all its chips in. And what that actually does is dramatically reduces the total computation speed for the algorithm so that it could actually respond faster than most humans would. I've got a graph of it later, but more so, it actually completely reduces the state space for the entire game down from 10 to the 160 to just 10 to the 7th, which in their paper, they say it's solvable within 5 seconds. using just a GeForce GTX 1080 GPU, which is less than $600 on Amazon, which is pretty amazing. Now, they used a little bit more hardware in training it. So this is basically the entire flow of how they will solve on every particular iteration. So on the left here, we have our total possible ranges. If you could read that at the top, it says 1326. Those are the total possible number of starting hands in a game of poker, where you have 52 possibilities for the first hand, 51, or for the first card, 51 possibilities for the second card. Divide that by 2, and it's 1,326 possible hands. They bucket those possible hands into 1,000 buckets, and that's how our ranges are determined. And then they feed that into a feed-forward neural net. For those of you who actually work in machine learning, you have a much better grasp of feed-forward neural nets than I do, because I just read the Wikipedia page. I'm not going to repeat that information for you here. But the idea is that training the game, again, like I mentioned, they limited the total possible actions to 4, and they randomly generated millions of poker scenarios, and the neural net then played itself against itself to determine all of the then possible actions to build those sparse lookup trees, so that when we're actually in the gameplay, we don't need the massive distributed cluster that they actually built up their neural net with. We just need the GeForce GPU local so that we could do the calculations to search it. They obviously, because of the randomness of how the computer was going to play, they put an invariant in there that suggests that any of the results of the computations must result in a zero-sum scenario, because if you were to think about it logically, you could actually wind up with the computer thinking that it was going to hit itself with a stalemate. And that's actually entirely possible in a game of Texas Hold'em. You could both have the same hand, or the board could be beating both of the players, and you end up splitting a pot. But we're interested in beating our opponents, not just tying with them. So we want to eliminate all of those other possible scenarios. And I actually reached out to the authors, but they haven't gotten back to me. I was wondering if, without the zero-sum neural net, exactly what would happen to this particular algorithm, whether or not it would actually lose or gain a little bit of an edge. I'm still waiting to hear back from them. But by applying all of our possible ranges as buckets and throwing them into the neural net, it spits out our counterfactual values that then give us, over all of these games that we played against ourselves, this is the probability of winning this much with this much at stake for these particular ranges, and so on and so forth. The results are a little bit interesting. So I should have worked on this slide a little bit more. But as you can see, on the left columns, we have the median and mean times for, at any given round in the game. So pre-flop, a human will take anywhere between 10.3 to 16.2 for the median and mean to make a decision, and so on and so forth. Decision times get a little bit quicker as the game goes on. But DeepStack is really, really fast. So the calculation results, the computation time specifically, made me wonder. So a lot of these online sites, they have both algorithmic and human monitors to try to detect cheating and bots and whatnot. Effectively, if you're not communicating with your opponent and you've taught a bot how to play Texas Hold'em, it could effectively be Turing complete. And I could think I'm playing against a human. But with DeepStack thinking so quickly, you would probably have to put random sleeps after every decision before actually even taking an action, just to try to trick people to think that you're actually human. But here's the results. So they basically offered a bounty of $8,000, I believe, to split across first, second, and third, and offered it up to 33 pretty high-profile professional poker players. And when they were training the algorithm itself, they discovered that you could find statistical significance in as little as 3,000 games played, which is pretty amazing because if you know any professional poker players that play online specifically, you could get through about 1,000 games in an hour, by playing multiple tables at the same time. If you got, multiple monitors, the sky's the limit. So on the bottom of this chart here, the bars represent the total number of hands played. And as you could see, and on the top shows the distribution of the win rate. Clearly the win rate shows a much larger range when we're playing much less than 3,000 hands. Anything under, even 300, the possibility for the computer to win versus the human to win is anybody's game. But the more hands that they played, up to about 3,000, we could see that with statistical significance that DeepStack actually won with a pretty significant margin. They're measuring it in MBB, big blinds, as we described earlier. And overall, their study showed that the algorithm won 492 on average big blinds per game, where 50 big blinds is, pretty much considered to be a huge margin in the game. So only 11 of the players out of the 33 actually completed the 3,000 hands for a total of over 44,000 total games played. So yeah, that's basically it. Anyone have any questions? So the question is, how large are the models? Do they fit all in one GPU's RAM at the same time? I don't know an exact sizing because the paper doesn't offer that. However, they do suggest that in real-time play, they were actually using a combination of 5 different GPUs. And obviously, that's why the thinking timing is, the paper suggested, roughly 5 seconds per decision, and we've got ranges from, 0.04 all the way up to almost 6 seconds. So the models themselves, I assume, are capable of fitting inside of a single GPU. And I mean, it's fairly, at the end of the day, that's an optimization that could be made, but it's not necessarily that much information, given that the neural net itself provides a lot of the sparse lookup trees for computing your opponent's counterfactual values for any particular given situation, and it trains itself over time. So, those should only slim down, if anything. So the question was, is there any discussion in the paper of betting as a signal and the psychological impact of the speed of processing time? No, there was not. Like I mentioned earlier, the paper actually didn't provide as much as I had hoped when I told Inez that I was actually going to do this paper. So what we can infer from the literature is that betting is an indicator because it's the only measure that we have from our opponent to approximate what their potential hold cards are. And this was a question that I also had when reading the paper, because how do you account for bluffing in a situation like this? So the function of bluffing, so like let's say that we were to have our strategy of playing against DeepStack. We're always going to bluff, right? That's a function of chance, of what we actually get versus what the public cards on the board are going to be. The betting is going to be indicative to Deep Stack of what sort of range we might be playing. For example, if in previous iterations when it was training itself, it noticed that betting within this particular range and raising in these particular situations revealed that there's a high probability that that the opponent's hole cards fall within these particular buckets, it's going to assume we have something that we're probably hoping to bluff with. So for example, if the flop was ace 3-2 offsuit and we bet that, there's going to be a high probability that either we're on a straight draw, we hit a straight, or we have an ace, and so. The statement was, if we were to randomize our betting, it would theoretically reduce the edge of Deep Stack's exploitability, or limited exploitability, rather. I think so, except over a long enough time, I think Deep Stack would still beat the completely random player, but unless we were to randomly play against Deep Stack, we don't really know. What we have to remember, though, is that it played, tens of millions of hands against itself that were all completely randomly generated, and so, despite the actions not necessarily being randomly decided, they were all based off of the past iterations of the traversal of the subtrees. It's reasonable to assume that it would completely crush a novice or a completely random player.
There was quite a disparity of the players that played all 3,000 games. That's how well Deep Stack did. Did they talk about the different strategies that those players used?
The question is that there was a large variance between the players who did not play all 3,000 hands. Oh, who did play 3,000. Right. So the question is that the players who actually completely played all 3,000 hands, there's a complete variance between 50 and all the way up to 1,000 millibig blinds. Did they discuss the different strategies that those players used? The answer is no. And I doubt those players would even discuss it themselves. So there was another chart that I didn't include that was in the paper that reduced the results to a luck adjusted win rate, but I didn't include that in a particular presentation specifically because they don't describe exactly how they adjusted the results for luck. So I mean, I suppose the luck would be getting dealt really, really good hands a non-trivial or statistically significant portion of the time. But again, they don't exactly provide that, so I couldn't include it. And I mean, I've thought about this as well. At the end of the day, if you they list in the appendix of the paper the 33 players who did play, and off the top of my head, I think 11 or 12 of them, their names were familiar to me. We're talking about guys like Phil Locke, who've played the WSOP 7 times, and several others. So, it is a very good question, and at the end of the day, there's also pseudocode that's available in the appendix. So, if you've got yourself a $600 GeForce, or a lot of time, and I don't know, maybe know something about TensorFlow or anything like that, you could probably try to recreate what they've done here. The paper is interesting to me because I love poker and I am a poker player, but it's actually more interesting to me because we're actually dealing with decision-making with incomplete information, which has applicability that has far more value beyond just beating somebody on in Texas Hold'em over a computer. And so the technique and the strategy that they use to reevaluate any potential situation while still trying to seek that Nash equilibrium is something that I think could be applicable to effective network routing for large-scale distributed systems, or other things that smarter people than me work on all the time. And so more so than the poker stuff is actually why I chose this paper. I really, really do wish, though, that there was a lot more detail that was presented, and like I said, I tried very hard to try to extract as much as I could out of it. So the question was, the people who played more seem to be doing better. Are the humans also learning about how DeepStack plays? That's a possibility. It's intuitive for a particular player to pick up on the types of decisions that your opponent's making in particular situations. Exactly, yeah. So the statistically insignificant results that are presented obviously for full disclosure, but unless this were to be, I would certainly love to see way more games played with more people and compare those results. I imagine that we would probably see a couple of different density groupings based off of average skill and so like let's say we were to take these 33 players, have them play 10,000 hands instead of 3,000 hands, and we were to pair them up with a control group of just random people that they found in a casino, as well as one more group of relatively average players. I would assume that the results presented here would show three separate density distributions that reflected the skill of the players against DeepStack in relative terms. Is the question, will we? So the question is, if we play 1,000 games against one player, is it going to use the same exact strategy against for the first and last game? Yeah, because we're not retraining against a particular opponent. So the answer to that is actually no, because we have variable change in the form of the chance of whatever card comes out. So unless the first and the last game or any other game is the exact same combination of cards as they've been shuffled, the results are going to be different, because what we're going to have is different possible counterfactual values for the opponent's hands. Yeah. So given the cards on the table, will it choose the same responses? Mm-hmm. So I'm not sure if any one player will play the same hand the exact same time, exact same way each time. But what you do have to remember, though, is if the betting varies despite the cards being the same, the DeepStack algorithm is going to respond differently, because the betting actions and the total pot size is a function, is an input to the function that it uses to calculate its next action. Right, it's not a repeated game strategy. Each game. That's what we assume. Good players will eventually try to learn what Deep Stack is doing exactly. However, I mean, like, that's effectively what all professional poker players end up doing is they, to the best of their ability, intuit a Nash equilibrium and look for, so like, the concept of perfect play is one that, assuming that we're not actually bluffing, for any given hand that I'm having versus what the board has, if the probability shows that I'm going to win at least 51% of the time, I'm going to probably play in a particular way. I'm sorry, I forgot what I was about to say. But yeah. So professional players, they all know, the odds for the most part, any given particular situation that they could find themselves in. What we decide to do, whether we, simply call a bet, or if we decide to raise or whatever, that's the information that really changes how we might actually respond. And what we're really doing is waiting for another player to slip up a little bit, or to change what we would expect them to, and that's how one player could take advantage of the other. And over a long enough timeline, that could result in, a significant difference between the two starting stacks. One last question? One last question. What's the question?
So like it says that it's winning somewhere between 50,000 of the big blind in each game played.
Yeah.
Is that good? Like if everybody's like a casino, how many big blinds are we winning per?
So, for a professional poker player who plays every day, they're grinding. So yeah, 50 millibig blinds, or 50,000th of a big blind is it's a good win, because over time that's actually going to add up to profit. If I go to a casino, I'm playing 2-5 stakes, I'm buying in for 500. I don't consider it a good game unless I win at least $1,500. So it's obviously going. How many hands? That's probably a 7-hour session, so I don't know, couple hundred? Yeah, less than 1,000 hands. Yeah. It is a little bit expensive, especially when someone, calls you at trips and then, rivers a boat. But yeah, thanks everybody. Yeah.
Yeah.